Okay, this is the November 2016 Physical Science Paper 1 multiple choice questions. It says the tendency of an object to remain at rest or continue in its uniform motion in a straight line is known as what? It is known as inertia. Acceleration is the rate of change of velocity. Newton's third law is about equal and opposite reactions. Newton's second law is about acceleration. So you can get confused with Newton's first law of motion, because if you have a look here, it says a body will remain in its state of rest or motion at constant velocity unless a non-zero force acts on it. That's the first law. So if you were looking for one of Newton's laws, it's easy to get confused. But inertia is actually the resistance of an object to change its state or motion. So if it tends to remain at rest or continue in its uniform motion, it is due to the inertia. Now it says to you here, 1.2, the mass of an astronaut on Earth is m. At a height equal to twice the radius of the Earth, the mass of the astronaut will be. And everybody leaps for Newton's law of universal gravitation and starts thinking, what must I do? What must I do? No. What is your mass? This question is about mass. This formula is for weight. The force due to gravity, Fg, is given by the law of universal gravitation. The only way to change the mass of the astronaut is if he chops off his arm, he chops off his leg, he chops off his head, or perhaps he urinates in his spacesuit. Then his personal mass will decrease and the mass of his spacesuit will increase. But mass is the number of particles in your body, and so his mass is the same on Earth as it is at a height twice the radius of the Earth. Mass is particles. 1.3, an object is thrown vertically upwards from the ground. Which one of the following is correct regarding the direction of the acceleration of the object as it moves upwards and then downwards? Ignore the effects of air resistance. Ignore the effects of air resistance. We have a projectile undergoing projectile motion, where the only force acting is the force due to gravity. And as we all know, gravity is caused by the fact that the Earth contains particles. Where does the force act? Downwards. It doesn't matter when the object is moving upwards or the object is moving downwards. The acceleration is always equal to g, which is always to the center of the Earth. Okay, if you look at this, what can you confuse this with? The other vector is the velocity vector. On this side of maximum height, the velocity has a positive vector, and on this side of maximum height, the velocity has a negative vector, if we say up is positive. But the acceleration is always the acceleration due to gravity, and it is always directed downwards to the center of the Earth. The answer is C. Whoops, we've skipped a question. Let's go back. 1.4. Now this is an interesting question. It says, a person drops a glass bottle onto a concrete floor from a certain height and the bottle breaks. There goes the bottle. Here is the floor. The person then drops a second identical glass bottle. You can clearly see it's identical. From the same height onto a thick woolen carpet. Here is the wool, but the bottle does not break. Which one of the following is correct for the second bottle compared to the first bottle for the same momentum change? Okay, so what is happening here when the bottle hits the floor? As the bottle hits the floor, it goes from some V to, when it's on the floor, 0. Okay, so momentum change, this is delta P, which is mvf minus mvi. But we have this formula that says F net delta T equals delta P. Now this delta P, the MV of the bottle just before it hits the floor, okay, well, when it's hit the floor and breaks, the MV is 0, and this MV over here, this is this one over here, just before it hits the floor, is going to be the same for both bottles because they're both being accelerated by gravity and they've got identical mass, so they have the same thing here. So this is the same for both bottles. What is the difference with this carpet issue? The difference with the carpet issue is that the bottle is going to take longer. The delta T is going to increase. Because why? The carpet slows it down with the hair. It's just like an airbag in an airbag collision in a car. You don't change your final velocity. You come to rest. You don't change your velocity just before the crash. So the change in momentum remains the same, but it takes longer, which means that if the time is longer, the force is smaller for the same change in momentum, because the change in momentum is how much MV did I have before I hit the floor going to nothing when I hit the floor. So what has happened? The average force is smaller and the time of contact is larger because all of those lovely hairs on the carpet are slowing down the bottle like an airbag slows somebody down in a car. So the answer is D. Okay, now here is a nice question that we could actually ask grade 10 because this comes from the grade 10 law of conservation of mechanical energy. It says a block of mass m is released from rest. So over here my velocity is 0. From the top of a frictionless, so we can have conservation of energy. Okay, a frictionless inclined plane QR as shown below. The total mechanical energy, remember that the mechanical energy is the sum of the potential energy and the kinetic energy. So it says the total mechanical energy of the block at EQ is EQ at point R and ER at point R. The kinetic energy of the block is KQ and KR. Well, before we go look at our options, okay, we are wanting, it says, which one of the statements regarding the total mechanical energy and the kinetic energy of the blocks is correct? Let's try and figure it out before we looked. What does the law of conservation of mechanical energy state? That the total mechanical energy in an isolated system will remain constant. So the short story is at the top of the block here, my potential energy is max and my kinetic energy is min, okay, adding up to my EQ. And on the ground here, my EP is nothing or minimum, and my EK is maximum. The energy is being transferred from potential to kinetic. But the total, the sum of these two mechanical energies, will be the same. So we can immediately lose this answer and this answer because this is an isolated system. The total mechanical energy will be conserved. Okay, so it's in the front at the top. I mean, it's in the front at the top. What am I saying? It is the same at the top as at the bottom. The energies combined, the mechanical energy, which is the potential plus the kinetic. However, if we look at the kinetic only, EK equals a half mv squared. So when we are at the point Q, the energy at Q is a half m0 squared, which is 0. When it's at the ground, it's going faster, so it will be a half mv squared, which means that this one must be larger and than this one. The kinetic energy over here is smaller. So which one of these little crocodiles? The kinetic energies can't be the same because the velocities are the same. It has to be answer B. The total mechanical energy is the same, but the kinetic energy is greater at R than it is at Q. The diagram below shows the positions of two stationary listeners P and Q relative to a car moving at constant velocity towards Q. So the car is going that way. The hooter of the car emits sound. Listeners P and Q all hear the sound. So what is happening? The car is pushing into its waves towards Q, and the car is moving away from its waves to P. So this end is going to be the high frequency, and this end is going to be the low frequency. Which one of the following correctly describes the frequency of the sound heard by P and Q compared to the driver? P is going to be hearing lower and Q is going to be hearing higher, so it is answer A. Let's look at 1.7. Two charges, plus Q and minus Q, are placed the distance d from a negative charge minus little q. The charges are located along lines that are perpendicular to each other. Which one of the following arrows correctly shows the direction of the net force? Remember, the net force is one force that has the same effect as two or more other forces, acting on negative q due to the presence of big Q and big Q. Okay, so we want to know, what does this fellow, negative q, little q, want to do? So we must always remember that like charges repel. So if we say, look at Q, he's in line with this negative Q, what will their interaction be? What will this fellow want to do? They will repel. So if they were attracting, it would move this way, but they are repelling. This is the force of negative Q on little negative Q. Then it says to you, so this is one force, yes, and we are trying to find the resultant or net force. So now we have to look at the other thing that can cause little q to move. Little q is negative, this big Q is positive, so they will attract. So negative q wants to move up. So if you have a look at the vectors, we can make a closed vector diagram out of this to find the resultant. First one, well, it's not a closed vector diagram, it's a head to tail vector diagram, I apologize. This is the force of negative q on little negative q, takes it to the left. This force takes it up. This is the force of plus q on little q. So how do we find the resultant? The resultant is from where we started to where we ended. So we started over here, we ended over there. Which arrow looks like that arrow? It is arrow C. Okay, learners investigate the relationship between current and potential difference at a constant temperature for three different resistors, X, Y, and Z. Well, the first thing I've spotted is that they are ohmic conductors because they are straight lines. They obtain the graph shown below. Now they want you to know about the resistances. The resistances of X, Y, and Z. Can you see here's the graph X, Y, and Z. What are their resistances? So most of the time you happily go, oh look, we usually use this formula, which is actually changed into R equals V over I. So if you know anything, you know normally when they do this, we are going to use the gradient of the graph to find the resistance, okay? But the gradient of the graph is the change in Y over the change in X. So in this situation, it is the change in current over the change in voltage. But this is not what the Ohm's law formula tells you. The Ohm's law formula tells you R equals V over I. So in fact, the gradient of this graph, okay, is actually the inverse of the resistance, 1 over R, because you have to flip this to find the resistance. So the ones with the steepest gradient, can you see this has got a steep or a large gradient? and this one has a small gradient. The gradient is the inverse of the resistance. So this will be the large resistance, and this will be the small resistance, simply because they plotted I against V, not V against I. So the correct answer here is A, because Z is the biggest resistance, followed by Y, followed by X. You have to be very careful and check your axes, what has been plotted on your axes before you can answer the question. Okay, 1.9. Which one of the following changes may lead to an increase in the EMF of an AC generator without changing its frequency? We know that to increase the EMF, we can increase the windings on the coil. We can increase the strength of the magnets. And what is the last thing we can do is we can turn the coil faster. Okay, but if we turn the coil faster, this is changing the frequency. So if we want the frequency to stay the same, we cannot do this one. This one would actually also decrease the EMF if we turn it slower. So what can we do? We can increase the area of the coil, because why? When we do that other sum, how do we find magnetic flux? E equals minus N delta phi over delta T, okay, from grade 11 when we do Faraday's law of electromagnetic induction. And this one is BA cos theta, where this is the field strength of the magnet, okay, and then A is the area of the coil. So if we increase the area of the coil, we will also increase the EMF without changing the frequency. And then 1.10, the wavelength of a monochromatic light source P, so lambda P is twice that of lambda Q. Lambda P is twice that of lambda Q. Am I writing this the right way? Okay, let me do this quickly. Lambda P is bigger than lambda Q, okay? So this means that the energy of a photon from source P, how do we find the energy of the photon? We go E equals hc over lambda, okay? So if we are doing this, the energy of P is going to be that. Let's read this question correctly. We need to check what's going on here. Is the energy going to be bigger or smaller? Well, let's just draw the picture. The wavelength of P, so if this is P and its wavelength, okay, here would be the wavelength, okay, is twice that of Q. So then Q is going to be like this. Yes, it will take two of these to make one of those. So if you've got a long wavelength, okay, you have a, look, it's on the bottom here. If you have a big lambda, you have a small energy, because E is inversely proportional to wavelength. Okay, so what will happen to the energy? It will be half the energy because it's got a long wavelength. So E equals hc over lambda. The trick I was having here is the wavelength of P is twice that of Q. So lambda P equals 2 lambda Q. So in actual fact, lambda Q is small and lambda P is big, which means the energy of P is small, because energy is inversely proportional to wavelength and directly proportional to frequency.